Hi everyone! Today we are exploring a mathematical tool that turns what looks like an algebraic nightmare into a simple trigonometric rotation. This is the De Moivre's theorem, the ultimate cheat code for complex numbers. Before we get into math, I want to set three clear goals for our next 10 minutes. First, we are going to define exactly what De Moivre's theorem is. Essentially, it's the bridge between trigonometry and algebra. And second, we'll learn how to apply it. I'll show how to take a complex number to a high power, like the 10th or 100th, without filling out 5 pages of sketch paper. And finally, we'll identify why this matters. This isn't just math for the sake of math. It's a tool used every day in fields like electrical engineering and digital signal processing. But before we look at the formula, we have to look at how it was discovered. De Moivre's theorem is named after Abraham de Moivre, a French mathematician born in 1667. Due to religious persecution, he moved to England, where he continued his mathematical work. In 1707, de Moivre discovered a pattern connecting complex numbers and trigonometric functions, especially when raising complex numbers to higher powers. This discovery later became known as De Moivre's theorem. Although de Moivre introduced the idea, it was later refined and made more popular by Leonhard Euler, who introduced Euler's formula. This formula shows a deep connection between exponential functions, trigonometry, and complex numbers. Today, de Moivre's theorem plays an important role in mathematics, physics, and engineering. Here's an interesting fact. De Moivre was so obsessed with math that he actually calculated the exact date of his own death. Notice he was sleeping 15 minutes longer every night and used a simple math sequence to predict the day he'd never wake up. And he was right. It shows that to De Moivre, the world wasn't just random. It was a series of patterns and sequences waiting to be solved. Now back to the math. To understand his theorem, we have to stop looking at complex numbers as coordinates on a grid like a plus bi and start looking at them as vectors with a length r and an angle theta. This is called polar form. By using the radius r and the angle theta, we turn complex numbers into something that looks like a rotating hand-on clock. Once a number is in this form, raising it to a power becomes much easier than doing standard algebra. This shift is what allowed de Moivre to find his famous connection. And to define de Moivre's theorem, we look at what happens when we raise a complex number to a power. Usually, in algebra, powers are difficult. They involve multiplying long strings of numbers. But de Moivre found a shortcut. He realized that if you are in polar world, the math becomes incredibly simple. Look at the formula on the screen. There are two things happening. First, the radius, or the length of our number, is raised to the power of n. If we are squaring it, the length squares too. But here is the magic part. The angle isn't raised to a power. It is simply multiplied. Geometrically, as we increase the power, the number is spinning around the center of the graph at a constant rate while its distance from the center grows or shrinks. It turns a complex algebraic problem into a simple geometry of rotation. Let's see in action. If I ask you to do 1 plus I times itself 10 times, you'll likely make a mistake somewhere in the algebra. But with de Moivre's theorem, it turns out much easier. It's basically just 3 steps to complete the calculation. Let's dive into some detailed calculations. First, we need to move from the rectangular world to the polar world. We plot coordinates 1, 1 on the complex plane. And using the Pythagorean theorem, the distance from the center, or r, is the square root of 2. Since the x and y values are equal, the angle theta is exactly 45 degrees. And now we apply the mover's magic. We take the square root 2 and raise it to 10 power, which gives us 32. Then we take our 45-degree angle and simply multiply it by the exponent 10. That gives us 450 degrees. And finally, we simplify. And finally, we simplify. A 450-degree rotation is just a full circle plus an extra 90 degrees. If you look at complex plane, 90 degrees point straight up the If we look at our complex plane, 90 degrees point straight up the imaginary axis. The cosine of 90 degrees is 0 and the sine is 1. So our final answer is 32 times I. No long-form multiplication. The cosine of 90 degrees is 0 and the sine is 1. The cosine of 90 degrees is 0 and the sine is 1. So our final answer is 32 times I. No long-form multiplication, no binomial expansion, just a few simple steps of rotation and scaling. This theorem isn't just work for powers, it works for roots too. If you look for the fifth roots of a number, they aren't just random points. Because they are equally spaced by the theorem, they form perfect geometric shapes. And the roots of a complex number form regular polygons, triangles, squares, and pentagons, hidden right there on the complex plane. And this symmetry is vital in fields like electrical engineering and signal processing. And now you might be wondering, when will I ever use this in real life? And the truth is, you are using it every time you check your phone. In electrical engineering, we don't just use standard numbers for electricity, we use complex numbers called phases. When engineers design the power grid or the circuits in your laptop, they use de Moivre's theorem to calculate how waves of electricity shift and rotate. And without this math, our modern power systems would be incredibly inefficient. And in signal processing, this theorem is the backbone of how we handle data. Every time you listen to a digital music file or use noise-cancelling headphones, a computer is using de Moivre's logic to break down complex sound waves into simple rotations. It's also how we compress images into JPEG files so they don't take up too much space. And finally, in the world of quantum physics, the tiny particles that make up our universe don't move in straight lines. They behave like waves. Scientists use these complex rotations to predict where an electron might be. From the massive power lines outside to the smallest atoms in your body, de Moivre's work is the math that describes how the world oscillates and spins. And to wrap things up, let's look back at what we've covered in the last 10 minutes. We define the theorem, moving from the standard rectangular view of numbers to a polar view. We define the theorem, moving from the standard rectangular view of numbers to a polar. We define the theorem, moving from the standard rectangular view of a number to a polar view that let us rotate through the complex plane. We applied to the formula to turn a messy algebraic expansion into a simple multiplication, and we saw how those answers form perfect symmetrical polygons. And finally, we identified its legacy from Abraham de Moivre's obsession with patterns in 1700s London to the complex wave analysis used in your smartphones today. De Moivre once said that math is the art of finding patterns, and I hope today you've seen the beauty in those patterns. And that's all. Thank you for listening.